So good morning all of you. Here in this video I am going to discuss the Ampere's law in differential form and integral form. Okay. So let us take a small infinite length wire which carries a current I. So this is my infinite length of wire which carries a current I. So like this, our current will be like this. It is coming out. It is coming out from the board. Okay. So this wire is an infinite length. In this infinite wire, current will be there. The current in this infinite wire is I. Okay, the magnetic field for this current is, by using right hand thumb rule, we can easily understand the direction of this magnetic field and current. So the magnetic field will be like this. So this is our magnetic fields. The magnetic field lines will be like this. Okay, see. See, by using the right hand thumb rule, we can easily understand. So if the thumb represents the direction of the current and these fingers curling, this represents the direction of magnetic field. See, it curl like this. And the thumb represents the direction of current. The current is coming out from the board. Okay, if suppose my current, if I am taking this coming out of the current is positive, for positive, the magnetic field lines, these magnetic field lines are in anti-clockwise direction. So the field lines are anti-clockwise direction. If suppose my current is like this, it is in negative direction, like this. That means it is going into the board like this. According to right hand thumb rule, the current, the magnetic field which produced by this current is in clockwise direction. See, like this. The curl is like this. So this represents, this symbol represents the current is into the board. The wire is like this. And the magnetic field produced by this current is like this. Okay. See, the field lines, now the magnetic field lines which produced by this current are in clockwise direction. If the magnetic field lines are clockwise direction, the current will be in negative direction. If the magnetic field is in anti-clockwise direction, the current will be in the positive direction. Okay. So now, so by using this diagram, this figure, we can easily conclude that the magnetic field lines, the curl of magnetic field lines will not be zero. We can easily say that the curl of the magnetic field lines definitely will not be zero. So like we have studied in electrostatics, the field lines, the curl of electrostatic field lines are zero, right? Why? Because if there is a positive charge, the field lines produced by this positive charge will be like this. It is diverging from the source charge. The field lines are diverging, right? We studied in our electrostatics. And which is converged at a negative charge. So like this. Our field lines are converging at a particular point. If we take a line integral from here, from this point to this point, if we take a line integral E dot dl, which gives 0, or if we took del cross E is equal to 0, we have seen that in electrostatics, right? The electric field lines does not form a closed loop, but here our magnetic field lines are form a closed loop. See, the magnetic field lines which produced by this current is form a closed loop. But there is not in the case of electrostatics. In the electrostatic field lines are diverging from a source charge, and these field lines will not form a closed loop. Okay. So then, so what is the effect of this magnetic field lines due to this current? Okay. So what is this magnitude value of this integral B dot dl? Let's see. So let us take a small length element dl. dl is a small length element here. The length element dl is at a distance s from the current. Okay. And in this region, in this dl region, the magnetic field is B. B is our magnetic field here. Okay. Then integral b dot dl. Integral b dot dl. I am integrating whole circular path. So for this dl, okay. So integral b dot dl is equal to integration b dl. Why? Because our magnetic field lines b and this length element dl are in parallel to each other, right? They form angle 0. The dot product of b dl, which gives b dl cos theta. Angle between them, this b and dl, is 0. So b dot dl can be written into b dl. Cos 0 is 1. So we can write this as b dl. But we calculated by using Biot-Salvers law the infinite wire. If we have an infinite wire, the magnetic field produced by that infinite wire is B is equal to mu naught I divided by 2 pi into d or s, the distance where you are calculating the magnetic field. Here I am calculating the magnetic field at a distance s. So this is my magnetic field which produced due to this current wire. Okay, so I am going to substituting here. So integral b dot dl is equal to integration of this b is mu naught I divided by 2 pi s into dl. So which is equal to mu naught I divided by 2 pi s into integration of dl. Our integration dl, if add this dl elements, we will get a circular for a closed circle. For closed circle, which gives the circumference of the circle. So that is the circumference of the circle is 2 pi s. Mu naught I divided by 2 pi s into 2 pi into radius. Our radius is s. So yes, 2 pi s and 2 pi s gets cancelled. So therefore, integral b dot dl is equal to mu naught I. So integral b dot dl gives mu naught into I. Okay. If suppose instead of taking a straight wire, if I have a bundle of wires which form a closed loop, so what will be our integral b dot dl? So let's see. So if suppose this is our closed loop, so if I have a n number of wires which pass through our closed loop, so like this. So these are our wires, okay, current wires. So like this, okay. So like this, then each wire, each current wire which enter into this closed loop will give mu naught I. That means the integral b dot dl is equal to mu naught into I enclosed. This I enclosed is nothing but total current enclosed in the closed loop. This is our magnetic loop. Integral b dot dl. This is our integral b dot dl. This integral b dot dl is equal to mu naught into I enclosed, the current enclosed in the surface. But the current coming out of the surface we are not taking. So we are neglecting this one. So I enclosed means if suppose this is I1, this is I2 and this is I3, then I enclosed is equal to I1 plus I2 plus I3. So this is our I enclosed. That means total current enclosed in this closed surface is equal to integral b dot dl. Okay. So this is our magnetic field which form a closed loop. Okay. So this is also the differential. This is also called as Ampere's law in differential form. We can also call it as Ampere's law. Ampere's law in differential form. Okay. Sorry, this is not a differential form. This is an integral form. Integral form. Integral form of Ampere's law. Okay, integral b dot dl is equal to mu naught I enclosed. Okay, let's see. Okay, if suppose our flow of charges is taken to be a volume current density. If our flow of current is taken to be a volume current density J, okay, then this I enclosed is equal to integration of J dot dA. Okay, next, but if our closed loop form a surface, then by using Stokes theorem we can convert this line integral into surface integral. Okay, so that is integral B dot dl can be converted into, by using Stokes theorem, integration del cross B dot dA. So this is my equation number 1 and this is my equation number 2. From equation 1 and 2, if you substitute this equation 1 and 2 here in equation number A, if you substitute equation number 1 and 2 in equation number A, see from the left side we have integration B dot dl. So in place of integral B dot dl, I am substituting del cross B dot dA. So integration del cross B dot dA is equal to, here in the right side I am substituting the value of I enclosed. I enclosed is equal to integration J dot dA. So mu naught into I enclosed with J dot dA. Okay, both are surface integral. So we can write this equation, we can reduce this equation into del cross B is equal to mu naught into this J. So this is an Ampere's law in differential form. We can call it as Ampere's law in differential form. This is very important expression, and this is also very important expression. This integral form of Ampere's law, which helps to calculate the problems, so many difficult problems we can easily calculate by using this integral form, Ampere's law in integral form, very simply. Okay, so this is this del cross B, the curl of magnetic field, which gives it is equal to mu naught into J. So this is differential form. Differential form of Ampere's law. Okay. In the next video we will discuss the divergent and curl of magnetic field lines.